Record. Hello everyone. So this video was on the request of some of my students who are doing AdMaths, and they wanted to get more of a feel for what they expect to do. So here we have a list of derivatives with certain functions and also the integrals of those relevant functions. Right? The integral is also called the antiderivative. So this may be very important as we would be using it throughout this class. All right, so if you were to pause the video, take note of it, or go back every time we need to use it, that would be fine as well. So let's jump into the questions. So first question, we are asked, given that y equal x cubed plus 2x squared minus 1, determine the coordinates of the stationary points and, of course, the nature of these points. Okay, so to get stationary points occur when the first derivative, or dy dx, is equal to 0. So let's just rewrite what y is. So y is equal to x cubed plus 2x squared minus 1. So if we were to differentiate it, so take the first derivative, we get dy dx is equal to, we use the standard power rule for derivative, bring the power out in front, right? Or multiply by the power by the number in front and subtract 1 from the power. So 3 by 1 is 3, so we get 3x, and if we subtract 1 from 3, we get 2. So we get 3x squared as our first leading term. Same thing here, 2 by 2, that is 4, and 2 minus 1 is just 1, so we have x to the first power. Now the derivative of a constant is 0, as you would notice here, where n is some constant, it is always 0, so we lose the last term. So this is our first derivative. Now what we want to do is set this equal to 0. So setting that equal to 0, we get the following: 3x squared plus 4x equals 0, and we can solve for x by factoring. This would be the quickest method. That is x into 3x plus 4 equals 0. And this gives us two cases. So if you have two numbers multiplying to give us 0, either the first one is 0, the second one is 0, or they are both 0. So we have either x is equal to 0 or 3x plus 4 is equal to 0. All right, so let's allow me to come here. All right, let's just finish this off here. So we have either x equal to 0, and we could solve this for x to get x, well, 3x is equal to negative 4. So that means x is equal to negative 4 over 3. All right, so these are our two x values. So if x equals 0, all right, this is our first point. We need to get the y coordinate now. All right, we just substitute it into y. So we have y is equal to x cubed plus 2x squared minus 1. So if you were to put 0 in there, we get 0 cubed plus 2 by 0 squared minus 1, which we will get to be negative 1. So the first coordinate, the first critical point or first stationary point, is the point 0, minus 1. However, if x is equal to negative 4/3, substituting that in, we get y is equal to negative 4 over 3 cubed plus 2 times negative 4 over 3 squared minus 1. We get negative 4 cubed. 4 squared is 16. 4 by 4 is 64. So we get negative 64. That's 16 by 4 is 64. And 3 cubed is 27. Plus negative 4 squared is 16. 16 over 9. But we are multiplying by 2. So we get 32 over 9. And, right, so 2 by positive 16 is positive 32. And then finally, we have minus 1. Right, we can get a common denominator here. So we can just put this over 27 one time. So we have like 27 over 27. Right, so 9, we can get a lowest common multiple here. right? If we were to multiply the top and bottom of this by 3, right? Because the LCM of all of them is 27. So we have everything over 27, negative 64 plus. Now, if you're not accustomed multiplying top and bottom by the number, we could have done it this way. 9 into 27 is 3. 3 times 32. 3 2s are 6. 3 3s are 9. And then minus 27. Yeah. All right. And then let's add up those things. We get 5 over 27. Right? 5 over 27. So this is our y value. So we have the second critical point is negative 4 over 3, comma 5 over 27. So these are our coordinates, our stationary points. So the stationary points occur at, the first one was 0, comma negative 1, and negative 4 thirds, 5 27ths. Cool. So the next part asks us to state the nature of the stationary points. So to get the nature of the stationary points, we have 3 possibilities. The first possibility is that is a maxima. So maximum if the second derivative, that's d2y dx squared, that is the derivative of the derivative, is less than 0. If it is less than 0, then it is a maximum. Minimum if d2y dx squared is bigger than 0, but if it is equal to 0, we have an inflection point. Right? If d2y dx squared is equal to 0. Now, this is a possible inflection point, but at this level, it is usually an inflection point. Right? We usually have to do the third derivative test. So let's just put this in a box and find what d2y dx squared is at the relevant points. So we have this as our dy dx, that is 3x squared plus 4x. So dy dx equal 3x squared plus 4x. And we want to differentiate this again. So we differentiating d2y dx squared, that will be, so put the power to the front, so we get 6x plus 4. Right, this would be our derivative of the derivative. And we would like to evaluate that at the relevant points. So at i.e. at x equals 0 and at x equal 4 thirds, negative 4 thirds. All right, so let's evaluate it at the first point. So d2y dx squared evaluated at x equals 0. That would be 6 times 0 plus 4, which is equal to 4. And what we need to note is that that is bigger than 0. So that we can write that right away. Minimum at x equal 0, and we could get the other one, d2y dx squared evaluated at x equal negative 4 thirds. So what would that be? So we have 6 times negative 4 over 3 plus 4, right? We could put that for like 12 over 3. Right? Maybe we could just leave it as 4. Yeah. So we have 3 into 3, 1, 3 into 6 is 2. So this is negative 2 by 4, that is negative 8. Negative 8 plus 4, that is negative 4. But what is that? That is actually less than 0. So that means maximum at x equal negative 4 thirds. Right? Since we have the derivatives being positive and negative respectively. Right? So this first point was a minimum, Right, this first point was a minimum and the second point was a maximum. Good. So we're on the last part of the first question before we start trying an integral. We have differentiate y equal 2x times the square root of 4 minus 8x with respect to x, simplifying the answer. So recall, if we have a function times another function, if we have h of x equal f of x times g of x, then the derivative, right, that's dh dx, or h prime of x is equal to the derivative of the first function times the second, plus the derivative of the second function times the first. Right? Notice we are taking derivatives one by one. So if we were to take the derivative now, right, the derivative, so dy dx of what we have there, y equal 2x times the square root of 4 minus 8x. If we were to take the derivative of the first function, we will get 2. So we have 2 times the square root of 4 minus 8x. That's the first part, that's this part, plus the derivative of the second part times the first. So allow me to just write 2x first, right? That's this piece. And we wanted to find the derivative of the square root of 4 minus 8x. Right, so we could use a substitution for that. So let's just do it at the side here. Let's say that k is equal to the square root of 4 minus 8x. So if we say let u equal 4 minus 8x, then du is equal to minus 8. Right, because the derivative of the 4 is 0. So then we have k is equal to, well, du dx, I should probably write here. Right, so then k is equal to the square root of u, right, which is u to the 1/2 power. So dk du is equal to 1/2 u to the minus half. But we know what u is this, but we do not want dk du, we want du dk, sorry, dk dx. So we have dk dx is equal to dk du times du dx. And this is called the chain rule. Right, so what do we get? We get dk du is 1/2, right, times the square root. Now this is minus exponent, so we can put it in the denominator. So we have 1/2 square root 4 minus 8x, because that is what u is, times du dx, which is negative 8 times negative 8. And that's our derivative for this second function. So we could put this into here. We have, just allow me to bring this around slightly. All right, so we have 1/2, right, square root 4 minus 8x, right, times negative 8. So we could cancel a few things. The 2's could cancel. The negative by the positive is a negative. So we could simplify this as 2 times the square root of 4 minus 8x minus 8x over square root 4 minus 8x. And this is our dy dx. Now you can go ahead and try to simplify this further, but I believe this is sufficient. All right, and that's our answer. The final question that we'll take a look at today is based on integration. Right, so we see the question says, show using integration at the finite area of the curve y equal sine x in the first quadrant bounded by the line x equal 4 pi over 9. Right, that's a little less than pi over 2. Is smaller than the finite region of y equal cosine x in the same quadrant bounded by the same line. So they say show by integration, but we could give a quick sketch of this graph. Right, we could give a quick sketch. So if we were in the first quadrant using sin x, right, we would have something looking like this, right, where this is 0, this is pi over 2. The second one, the cosine would look something like this. Right, it would look something like that in the first quadrant. So this one is sin x, and this one here is cosine. Right, but we want the line 4 pi over 9, that's this piece here. Right, that's this quadrant. So this is about 4 pi over 9. Right, roughly. But we cannot tell anything directly from the graph. We would prefer to use the integration. So we could set up our integration. So we want to check the integral. Now, the first quadrant extends from 0 to this line they want, which is 4 pi over 9. And I will use this time to say that this is in radians. You need to use radians, not degrees as some of our calculators are in. And then we have sin x. Right, so we have the first area. So let's say that this is a1 and we have dx. Now the integral of sin x is minus cosine x. Right, so that we could go back up and look at that. Right, the integral of sin x is minus cosine x. We can ignore the constant of integration for now since we are integrating with respect to our limit. Right, if we were not integrating with respect to our limit, we need to keep the constant. So we have minus cosine x, and we want to evaluate that from 0 to 4 pi over 9. So if we were to do that, we have negative upper limit first. We have cosine of 4 pi over 9 minus cosine of 0. Upper limit minus lower limit. And what do we get? We get cosine of 4 pi over 9 is approximately 0 point. So we can just use a quick approximation. 0.174. Right, so don't forget the negative all the way out in front. Right, so we have negative, open brackets, 0.174, and cosine of 0 is 1. So what we have here is that this is equal to negative 0.826, which of course is positive 0.826. So the area between sin x and the x-axis in the first quadrant, bounded by the lines, is 0.826. Similarly, we could do the area 2, which is the cosine one. So we have integral 0 to 4 pi over 9 cosine x dx. Okay, and we can integrate that. And what do we get when we integrate it? We get sin x, right? The integral of cosine x is sin x, and we want to evaluate that from 0 to 4 pi over 9. Same idea. We could substitute the first value first. We have sine, there's always upper limit minus lower limit. We have sine of 4 pi over 9 minus sine of 0. And sine of 4 pi over 9 is approximately 0.985, and sine of 0 is 0, so this is equal to 0.985. So we can clearly see that A2, so this is A2, this is A1, A2 is clearly larger than A1, which means or implies that the area bounded by the curve of sin x and cosine x is larger, right? So we could say hence proven. And so hence proven by, of course, integration. Okay, and we have our last example, right? I would like to leave these other questions for another video because I do not want to make it too long. Right, so here we have the finite region in the first quadrant bounded by the curve y equal x squared plus x plus 3. And the line x equal 4 is rotated completely about the x-axis. Determine the volume of the solid of the revolution form. Okay, so if we were to just graph this quickly, write a little rough sketch. We have a minimum point before it cuts the y-axis, and notice that it doesn't cut the x-axis because this is always positive. So we have a graph looking like this, right? Where this is 3, this is 0, and about here is 4. So we'll give here 4. Now, if it was to rotate about the x-axis, we'll have something looking like this. Right, and the rotation would look something like this. Now remember, we are only going from this point to 4. So this is our speaker looking sketch here. So this is what we want to find, the volume of this thing. Now notice that this is circular. So the area of a circular piece of something is pi r squared, right? But notice it's not the area we want. We want the volume, right? So we want this perpendicular height here as well. Okay, so notice that this r squared is not a constant, or this r is not a constant. So this will be some function of x. And interestingly, that is actually our function y. Now, it's not the area we want. We actually want the volume. So the volume of this thing is the integral between the limit, which is 0 to 4, times the area, well, the integral of the area of our region. And what is this? This is the integral from 0 to 4. A, which is pi, we can take the pi out, it's just a constant multiple. R is x squared plus x plus 3. And we would like to square that. We have the x. Okay, so we can square this quite easily using the formula. So what do we get? Right, I'll just write what we get. Okay, so this is what we get when we expand it out. So you can expand it out on the side, right? X squared plus x plus 3 by x squared plus x plus 3, right? If you need to do that. And we would get, after integrating, we have the pi out in front still, open brackets, add 1 to the power and divide by the new power. That's the power rule for integrals. So we have x to the 5th over 5 plus 2x to the 4th over 4 plus 7x cubed over 3 plus 6x squared over 2 plus 9x. And we want to evaluate that from 0 to 4. All right, so just allow me to clear up some of these things. So our volume, right? Notice if we plug 0 in, it would be 0 because all of them have an x term in it. So all we need to do is plug in the 4. So we have pi into, we have 4 to the 5th over 5 plus, now this is, we can cancel this down a little bit to be 1, 2, right? Or you can notice that this is actually 4 to the 4th power divided by 4. So this would be like 2 times 4 cubed plus 7 times 4 cubed over 3 right? So let's just write that properly. 7 times 4 cubed over 3 plus, this could cancel down a lot. So we have 2 into 2, 1, 2 into 6 is 3. So we have 3 times 4 squared plus 9 times 4. And what would that give us? The volume would be Right, so you would see this come out to be around 566 times 2 over 15 pi units cubed. Right, so this is our cubic units. And this is the end of our class, our little revision session today. All right, so I will leave the computation to you all. You could verify that for me and let me know in the comment section. So thank you for coming. And in our next video, we'll take a look at part C, which asks us to find the equation of a curve given the gradient and kinematics using integration and whatnot. And of course, we have our displacement or distance time graph. Right, so that's it for today. Thank you for coming, and I'll see you all in the next video.